So this is atomic structure. Now, when we are discussing atomic structure, basically what we are talking about is an atom. Now we know when we are talking about an atom, the basic parts of an atom, we are going to have electrons. Electrons are located in shells. We are going to have also the nucleus, where we have got positive protons and neutral neutrons. These neutrons don't have any charge. Okay. Now, when you're talking about an atom, it has got limitless number of shells. In other words, the shells continue to go on and to go on. If you have got an atom which has got one electron, you are only going to show one shell. Okay? Not because that atom has got only one shell, but because you don't want to show empty shells. In other words, you can't show the shells of an atom. You can only show those which have been filled up. When you want to find the number of electrons in each shell, electrons will be given by 2n to the power 2. So for the first shell, we say that n is equal to 1. Electrons will be 2 times 1 squared, which is just 2. Second shell, electrons will be 2 times 2 squared, which is 8. For the third shell, just like that, 2 times 3 squared, that is going to be like 18, and you continue to move like that. That is how you determine the number of electrons in each shell. We have got something which is known as a proton number. Proton number is also known as the atomic number. So this atomic number is just showing the number of protons, these positive entities which are in an atom. We also have the mass number, also known as the nucleon number. This one is showing the number of protons. So for protons, we use the symbol, that should be the symbol Z. So we are going to be adding the protons and the neutrons to get the mass number. Okay. So therefore, the mass number, that's not even symbol Z, that should be A. So the mass number, therefore, Z is going to be the atomic number plus the nucleon number. Anyway, please try to check should if I've just confused these two numbers. Okay, but it's actually I've confused them, so it should be like this. The proton number is Z, mass number should be A. In case there is a confusion, you can still confirm that anyway, but it's not that vital for you to know. It can't affect your marks. So how an atom is going to be shown on the periodic table is an atom on the periodic table. Let's say I've got an atom A. It is going to have a mass number and also the proton number. It doesn't matter which one is on top, which one is down, but you are going to see that the proton number is going to be smaller than the mass number, like that. Now, what happens is this: when you have got, let's say this is your atom, it has got these shells. Say you have got an electron in the first shell, that is an electron. What will happen is this: when you give this electron energy, you hit it with energy, and this energy is going to be in form of light. Now, just like the basic quantity of matter is an atom, light is made up of what is known as photons. Just like living cells have got cells, light have got photons. So what is going to happen is that when you project energy in terms of light or photons on an electron, when an electron gains energy, it is going to transition. And the meaning of transitioning is that it is going to jump from one energy level to a higher energy level. So see what happens. It has jumped from a lower energy level, it has gone to a higher energy level. Now, when you had an electron which was in a higher energy level, this electron loses energy. What will happen is that it will drop to a lower energy level. When energy is being lost, we use a negative sign to represent it. So when you see energy with a negative, it means it's being lost. Positive, it means it's being gained. So from this same knowledge that you are able to see here, we can actually calculate the energy that an electron can lose to transition between energy levels. Let's say an electron, let's say an electron is in, say, the second energy level or anything. Okay, let me just say it is in the second energy level. Okay, let me say it is starting. So we're going to be using N1 and N2. N is representing the shell in which that electron is. Please take note, N is representing the shell in which that electron is. Let's say an electron at the beginning is in the fourth shell and then it ends up in the second shell. Now, a very direct and simple question. If an electron was in the first shell and then it went in the second shell, did it gain energy or it lost energy? Anyone to answer us? Very good. It means it has lost energy because moving from a higher energy level to a lower energy level is a loss of energy. So, what happens is this. Let's say in the third energy level, electrons in the third energy level have got 6 joules of energy. Electrons in the second energy level have got 4 joules of energy. Electrons in the first energy level have got 2 joules of energy. What will happen is that when you give 4 joules of energy to an electron in the first energy level, it will go to the second energy level. This same electron that is in the second energy level, if you give it, first energy level, if you give it 6 joules of energy, it will end up in the third energy level. So, meaning if this electron which is in this first energy level, you give it 5 joules of energy. Anyone to guess, if I give it 5 joules of energy, where do you think it is going to be? Anyone? So we have got an electron in the first energy level. You give it 5 joules of energy. Okay, so between the second and the third, that's your answer? Okay. Is there is there anyone who has got something different or we are all thinking of the same? The first one, remember what we are saying is that the energy in the first is 2 joules, in the second is 4 joules, in the third is 6 joules. And then you give an electron in this shell, let's say the first shell, you give it 5 joules of energy. And you know that when you give an electron energy, it will go to a high energy level. So if I give it 5 joules of energy, in which energy level is it going to go? Someone has said it is going to be between the first, the second, and the third. Anyone else? No other idea? In the third? Okay. Anyone else? I, it's Annie and Harry. Please, you can go on. Okay. Okay. Thank you. Any other idea? Okay, so what you need to understand about energy on this topic is that energy is quantized. And the meaning of this quantized is that it exists only in specific values. You can't find a number in between. If you have got 2 joules of energy, the next is 4 joules, the next is 6 joules. You can't find anything in between. So what will happen is that if I give this electron in the first energy level 4 joules, it will go into the second. If I give it 6 joules, it will go into the third. If I give it 5 is not belonging to any energy level. What will happen to that energy I'm giving it? It will simply pass. That light will simply pass. It will not affect this electron. That is the meaning of quantized. So you can explain it looking at stairs. Stairs are quantized. It's either you step here, or you step here. You can't step here. It's different from an incline. For an incline, you can step anywhere. Okay, so that is the meaning of quantization of energy. So you can actually calculate the energy in an energy level using the equation which was given by Raydig. So to be able to calculate the energy in an energy level, energy is given by proton number. So before the proton number there, we are going to have negative R multiplied by proton number squared divided by the shell number squared. Now, because on this topic we only deal with atoms which have got a mass number of 1 actually, like helium and hydrogen. Where there is Z, we always use a 1 there. So therefore the equation changes to become negative R. Now R is known as a Rayleigh constant, and it is negative 2.178 times 10 to the power negative 18 joules. It's either you know it or they'll give it in the exam paper. But you see, the more you practice with questions, you are going to know it. So it's a small number to know. And then where there is Z, because proton number is 1, and then n squared. So this becomes the formula to calculate the energy in an energy level. If I put 1 where there is n, I'm going to get this same value as the answer. If I put 2, the answer will be becoming bigger and bigger. Now the thing is this, for negative numbers, when the number is becoming smaller, it's actually becoming bigger. So if you are dividing a number by a denominator, the more you increase the denominator, the smaller the number becomes. But because there's a negative in front here, the more you divide by the bigger the denominator, the bigger the number will be becoming. Okay, like that. So meaning that a first shell has got electrons with the lowest possible energy. If you want to calculate the energy now, that is going to either be gained or lost for an atom to transition between energy levels. Energy is going to be given by negative 2.178 times 10 to the power negative 18 joules, and then you get 1 over, you say the final energy level squared minus 1 over the initial energy level squared. So for this example, we are transitioning from the fourth energy level to the second energy level. So therefore it becomes negative 2.178 times 10 to the power negative 18. 1, the final energy level is 2. Square that, minus 1 over the initial energy level is 4. Don't forget to square that. What you just want to do here is to punch this on the calculator, and then you'll be able to get, if you punch that, you'll be able to get a negative 4.084 times 10 to the power negative 19 joules. Okay, so this is going to be the energy. This is actually joules per photon. What we mean by photon is the photon is the amount of light that you are projecting on that particle for it to be able to transition. But we just write it as joules like that. We don't include this. Is this okay? And you can see the answer is negative. Remember we said the only way an electron can move from a higher energy level to a lower energy level is if it loses energy. if we changed where there is 2, we had put 4, and then where there is 4, we had put 2, it means that something is moving from the second energy level to the fourth energy level. The answer will actually be positive, and that means that an electron had to gain energy. Does this make sense? Okay. Now, if you look at energy levels, say here is your first energy level, here is your second energy level, here is the third energy level, the fourth, the fifth. You can see the more we move away from the nucleus, the lower the distance between energy levels. So that distance between energy levels is actually called the wavelength. Okay, the distance between energy levels is called the wavelength there. So you can actually calculate the wavelength when you project light and then an electron transitions between an energy level to another. But before I talk about that, when an electron moves from any energy level going to the first energy level, from any, as long as it's gone to the first energy level, meaning that energy is going to be lost, that is known as the, so every time it is transitioning going down, not in the opposite direction, that is known as the Lyman series. When an electron transitions going to the second energy level, it doesn't matter where it's coming from. That is known as the Bauma series. When an electron transitions to the third energy level, it doesn't matter where it's coming from. That is known as the Persian series. When the electron goes to the fourth energy level from wherever it can come from, that is known as the bracket series. And then if it goes to the fifth energy level, that is called the P-fund. So sometimes they can just tell you an electron that is in the, let's say, fourth energy level transitions in the Balmer series. Calculate the energy, okay, that is lost. So already immediately they mention Balmer, it means that it has now gone to the second energy level. Now the question is, how do you calculate the wavelength that is going to be between two energy levels when you are talking about the transitioning of these electrons from one energy level to another? So there is another equation that you use similar to the same one that I'm just from showing you here. So in this case, we are going to find what is known as a wave number. Something that you need to know about a wave number is that wave number, you write it like this with a dash on top, is 1 over wavelength. And this wave number is going to be given by the rate d constant, but you can see this rate d constant, I've put h there. This is the rate d constant that we use for wavelength. There is the rate d constant that we use for energy. They are different. So this is going to be given by RH multiplied by 1 over n final squared minus 1 over n initial squared. Okay, and this RH here is 1.09 times 10 to the power 7 meter to the power negative 1 is per meter. More likely, when you have been given such a question, you'll be given this constant. If they don't give you, it's not a number too hard for you to know, but more likely they are going to give you. So now, how do you calculate the wavelength? So let's say light hits an electron that is in the third energy level, and that electron transitions and goes to the second energy level. You want to be able to find the energy that is going to be able, we want to find the wavelength of that light which had to hit the atom to move from the third energy level to the second energy level. For you to be able to do that, what you actually do, you simply use the same equation here. You can first capture the wave number. So wave number is going to be equal to RH, so where there is RH, you put 1.09 times 10 to the power 7, and then multiply by 1 over the final energy level is 2, so that will be 2 squared minus 1 over the initial energy level is 3, so that is going to be 3 squared. If you punch this one, the calculator should be able to get 1523611.11. But remember, this value here was in meter to the power negative 1, so meaning that the unit for this one will be meter to the power negative 1. But our question is want to capture the wavelength, not the wave number. So wavelength is the reciprocal of the wave number. So the wavelength is 1 over wave number from this equation, which is here, this part. So this will become 1 over the wave number is 1523611.11 meter to the power negative 1. If you punch this on the calculator, it's going to give you 6.56 times 10 to the power negative 7. The meter was in the denominator and it had a negative power. So if it goes up, it will be having a positive power. Now, mostly we leave these answers in nanometers. So what you do is multiply. We have a meter on top, we put a meter down, and then a nanometer on top. A meter is bigger than a nanometer, so we'll put 1. Nano is 10 to the power 9. If you multiply this, you are going to get 656 nanometers. So this becomes the answer. Is there any question? I've seen a hand. Please, you can go on. Okay, seems there's no question. Okay, the next thing that we need to understand is something which is known as Heisenberg's uncertainty principle, or the uncertainty principle. Now, the uncertainty principle, look at this. I'm going to give an example that we know. If imagine, think of a box like this one, okay? And then you have got a ball, say a ball is like this. And then you have got an electron. Now you know how small an electron is, okay? Here is an electron. It is very small even in comparison to this. So if you get these two guys, you put them in the same box. For a ball, it will cover up the space like that. Hope hope you are able to see. Okay. Are you able to see now? Sorry, I had to. Can you now see? Are you able to see now? Are you now able to see? Can someone confirm if you can see now? Okay. So, the are we on the same page? Or maybe I lost you from somewhere else. Okay. So I was saying, imagine you have got a ball, a tennis ball, this one, and an electron. If you get the tennis ball you fit in this box, look at the way it's looking. And then now get an electron you put in this box. There. Imagine this box is like very small. Let's say we got a very small ball. Okay, not even a tennis ball, a very small ball, which can fit in a distance of 1 centimeter. Now, an electron, even in a distance of 1 centimeter, will look to be very small, but 1 centimeter is very, very small. That is because electrons are going to be measured in much, much more smaller units because of their small size. So, at least for the ball, you can know okay, this ball might be somewhere, let's say 0.7 centimeters. But for the electron, because of its small size, it's very easy. I mean, it's very hard for you to know its exact position. Now imagine this electron moves from this point, it goes to that point. You can actually, because the distance looks to be a bit big, you can find its speed. Okay? You can find its speed. But for this ball, imagine it moves up to this end, to the end of this box. You will not be able to know its speed because it's more likely like you can't even tell that it moved. So what are we saying? For the ball, we know its position, but it is hard for us to know its speed when it moves. For the for the electron, we don't know its position, but we can easily know its speed when it moves because it's small. And the speed, which is velocity multiplied by mass, gives you what is known as momentum. So this is what Heisenberg's uncertainty principle tells us. Heisenberg's uncertainty principle tells that we cannot measure the position and the momentum of a particle simultaneously. If you know the position, you will not know the momentum. If you know the momentum, you will not know the position accurately. In other words, you say Heisenberg's uncertainty principle states that there is a fundamental limitation to just how precisely we can know both the position and momentum of a particle at a given time. There's a fundamental limitation to just how we can know both of them. And the principle is going to be given by an equation. If you get the change in position, which we're going to refer to as x, position will be referred to x, you multiply by the change in momentum, which is going to be given by p. It is going to be greater than or equal to Planck's constant divided by 4 pi. This h you can see is a constant known as Planck's constant. So this becomes the equation for this one. Okay, like that. So imagine you have got a particle which has got a mass of 2 kg, and then the uncertainty delta x and delta p, you can see the uncertainty in position and uncertainty in momentum. Let's say it's uncertainty in momentum, okay, is 0.15 meters. It's actually kg meter per second. That's the unit for momentum. You want to find the uncertainty in position. How can you find it? How can you determine the uncertainty in position? So you can just come here, make delta x subject formula. So divide both sides by delta p. So therefore delta x will be greater than or equal to h over 4 pi and then multiplied by delta p. This will give you delta x being greater than or equal to h, Planck's constant. This is a constant as you can hear. So that will be 6.626 times 10 to the power negative 34 divided by 4. We know pi is just a number, multiplied by delta p. Now that delta p change in the position is what we've been, I mean change in the momentum is that what is there, which is 0.15. So this will give us a number that is greater than or equal to, like, that is 3.86 times 10 to the power negative 4. The answer will be in meters because this is position. So that is what is known as the Heisenberg's uncertainty principle. Okay, now besides this, there's something that is very important that you need to understand. So if you've heard of Einstein, okay, anyone who has heard about Einstein, anything that you know about this man, anything or no idea? So Einstein gave us the relationship between light, actually the mass of a compound, and energy. So he told us that anything that has got mass is going to have energy. And he said that energy is going to be equal to mass times the speed of light squared. This is the equation that Einstein gave us. And then another person gave us another equation, and he said, oh, actually, and this was Planck. Planck gave us another equation, and he said, actually, you can determine energy of something by just saying energy is equal to Planck's constant times the wavelength. Now, on this topic, uh, Planck's constant not times wavelength but times frequency. On this topic, frequency, normally in physics we use frequency, we use F. But specifically on this topic, you will not see F. What you see is no. It looks like a V. This is a symbol for frequency. H here is known as Planck's constant. So look at this. Anything that has got mass is known as a particle. And in high school, you learned that a wave, the properties of a wave is that it has got wavelength, frequency, and speed. Because this one has got a wavelength, it means that it is a wave. So what does this tell us? It means that energy is both a particle and a wave. That's the meaning. Now, another person who is known as Louis de Broglie, okay, came and combined these two equations. So what he did, since energy is mc squared and energy is Planck's constant times frequency, he actually combined them, and then he said mc squared is going to be equal to Planck's constant times the frequency. Another thing that you need to know about frequency is that when you have speed of light is going to be given by wavelength times the frequency. Okay, this will give us the speed of light. Now remember, we are saying frequency will not use F. So speed of light will be wavelength times frequency. Frequency will use this symbol. So I can make frequency subject the formula. So frequency therefore becomes speed of light over wavelength. So he came and substituted, it became mc squared is equal to Planck's constant, where there is frequency, he put speed of light over wavelength. So you need to be looking at these equations because they can give you a question where you are supposed to use one of these equations. And then at this point, it did cross multiply. So what was found was mass, wavelength, speed of light squared is equal to Planck's constant times the speed of light. So at this point, we can divide both sides by C. You can see one C will cancel this side, so we are going to remain with mass, wavelength times C is equal to Planck's constant, like that. If I want to remain with the wavelength alone, I'll divide both sides by mc. Okay, and so that gives us wavelength being equal to Planck's constant over mc. Now remember, c is the speed of light. What Louis de Broglie did is that he said, okay, why not just use any speed instead of only the speed of light? So the equation became therefore wavelength is equal to Planck's constant divided by mass times velocity. So this one is known as the de Broglie equation. Now, mass times velocity is also known as momentum. So he also said that wavelength is Planck's constant over momentum, and momentum is p. So there, they can give you Planck's constant is a constant, so it's 6.626 times 10 to the power negative 34. They'll give you the mass, and the mass of an electron is a constant. It's 9.11 times 10 to the power negative 31 kg. They'll give you also this value in case you are talking about an electron. Okay, imagine light which is moving at a speed of 30 meters per second. hits an electron, what would be the wavelength of that speed of light? So all you do is substitute where there's Planck's constant with 6.626 times 10 power negative 34. Where there's mass, the mass of an electron is given there, and then the speed of light is given there. You find the wavelength, and wavelength is given in meters. That is how you calculate. So this equation, because it combines, okay, if you look at this equation, it is showing that you have got mass there. You also have speed of light. Anything that has got mass, remember, is a particle. What has got speed is actually speed is one of the properties of a wave. So this is also known as the dual nature of matter. So this tells you that matter is both a wave and a particle. That is what Louis de Broglie said, that matter is both a wavelength and a particle. Okay, you can have some questions to say, let's say we have got an example. Calculate the de Broglie wavelength of a ball that has got a mass of 75 grams, and then it is moving at a speed of 42 meters per second. Okay, no, not really the mass. Okay, we can use that one. So the question is, what is the de Broglie wavelength of a 75 grams ball moving with a speed of 42 meters per second? To be able to do that, we know that wavelength is a Planck's constant over momentum, and momentum is mass times velocity. So Planck's constant is 6.626 times 10 to the power negative 34 divided by mass. Mass should always be in kg, so 75 divided by 1000 to be 0.075 kg, and then multiply that by the velocity, which should be always in meters per second, which is 42. And this is going to give us 2.1 times 10 to the power negative 34. Wavelength is in meters. Please, every time they've given you a unit that is not an SI unit, make sure that you convert to the right unit. So this is how you deal with the de Broglie wavelength. Now, another concept that you need to understand is known as the photoelectric effect. The photoelectric effect. It's a very important concept you need to understand. Now, how about the photoelectric effect? So imagine you have got a metal. Here is a metal. So what happens is this: when you project heat on this metal, on the surface of this metal, say you project heat on that surface, what will happen is that electrons will start to move out of the metal surface. Okay, that is what is known as the photoelectric effect. So if they ask you, state the photoelectric effect. When light strikes the surface, please, not just a metal, but the surface of a metal, electrons are going to be emitted. That is what is known as the photoelectric effect. Now, this is, of course, energy that is projected, and we are saying specifically light. Now, we said the units for light that we talk about are photons. So, any one of these words can be mentioned. Whether they mention energy, light, or photons, all the same. But one thing that you need to understand is that not all energy that hits the surface of a metal cause electrons to move away. Already we've said that energy is actually a wave, meaning that it's going to have a frequency. And we are saying frequency is given by this symbol nu. So electrons only be able to move out of the metal if that that energy that is hitting the surface of this metal meets a minimum. So the minimum frequency that you need, of the minimum frequency of light that you need to project on the surface of a metal for electrons to be able to move out is known as the threshold frequency. Okay? Threshold. It's the smallest. Now remember, we said that energy is actually Planck's constant times frequency. So if I multiply by the threshold frequency is given by this same nu with a zero down there. That is the threshold. So the energy that I need to project on the surface of a metal for electron to be able to move out to be Planck's constant times nu. Okay, and then electrons will be able to move out. And this is nu with a zero. That is the threshold frequency, the minimum frequency of the light. Now imagine the energy that I projected on this metal has got a frequency greater than this one. Okay, let me give an example. Imagine for this metal, the threshold frequency that you need, let's say the threshold frequency that you need is 2 Hz. Okay, like that. And then imagine you project now light which has got 4 Hz. Okay, what will be the energy first? The energy with the threshold frequency and the energy with this frequency that you've projected. So energy with the threshold frequency is going to be called the threshold energy. That is the smallest energy that you need to project on the metal for electrons to be able to move out. So that will be equal to Planck's constant, which is 6.626 times 10 to the power negative 34. That will just be multiplied by a 2. We'll get a value there. And then now, because we're projecting 4 joules of energy, the actual energy that we are going to have is 6.626 times 10 to the power negative 34. Now multiply that value by a 4. Let me just want to get 6.626 times 10 raised to the power negative 34. Then we are multiplying this. Okay, times 2. So if we multiply by 2, we're going to get 1.325. This is not even 1 point. Let me write it again. Okay, so we're going to be able to get 1.32. Let me just admit someone first. Okay, 1.32 times 10 to the power negative 33. This is going to be in joules. Remember, this is energy. Now, let's say we put now a 4 there, we multiply by 4. So if we multiply by 4, the value that we'll be able to get is going to be 2.65 times 10 to the power negative 33 joules. This is the amount of energy that we have projected on the metal. This is the minimum energy that is required to move electrons from the surface of a metal. So there's actually going to be some energy which is going to remain. So that energy that is going to remain, okay, that energy difference is going to be found by the energy that you are projecting, which is 2.65 times 10 to the power negative 33. You remove minus 1.32 times 10 to the power negative 33. Anyone who can punch that to help us? 1.32. Okay, so this is supposed to give us negative. Is my calculator giving me the right thing? Okay, it's not giving me the right thing. Let me not even punch so that it might waste time. You punch when you are in the exam. Let me explain concepts so that you understand. Okay, just imagine the answer that would have gotten here. Let's say I'm going to use a small number. Let's say we had gotten 4 joules. I know this is not the value that you get. Okay, imagine we got 4 joules when we subtract. This energy here on top is the minimum energy that you will require to move electrons. Now you have projected energy which is more than the minimum required to move electrons. So this is the extra energy. The question is, this extra energy, what will it be used for? So this extra energy will be used to determine this how fast the electrons will be able to move from the surface, how fast. So the extra energy will determine the kinetic energy of electrons. Now you know that kinetic energy is given by half mv squared. So we'll get that energy that we found, the extra energy, which is 4. And that will be equal to half. We know that these are electrons moving. The mass of an electron is 9.11 times 10 to the power negative 31. Okay, times v squared. So if we make v squared sub the formula, we're going to have 2 multiplied by 4 divided by 9.11 times 10 to the power negative 31. To remain with v, will square root both sides. So if you punch this on the calculator, the v that you are going to find is going to tell you how fast electrons will be able to move from the surface of the metal, and that is going to be in meters per second. So this is how you can determine the speed at which electrons will be moving from the surface of a metal. Don't forget that for the photoelectric effect to be possible, you need minimum energy, all right, and you need minimum frequency. Another thing that you need to know is that for light with frequency that is greater than the threshold, the extra will be used for kinetic energy. Do we have any question here? Any question? I bet it's clear enough. Okay, very good. Now let's talk about what might be so confusing. Electronic configuration. This is not the electronic configuration that you did in high school where you were saying 2 comma 4 comma. So if they ask you to write the electronic configuration, you don't write 2 comma what. Okay, there's a specific that you are writing. Now, for you to be able to understand how to write electronic configuration, you need to understand that when you're talking about an atom, okay, in these shells that you see, electrons, think of it. If I say, Harry, where are you? If you say I'm at home or in the house, that is, if you say I'm at home, you're not being specific. Okay. Or let's say you say I am in the house. You are not specific where exactly. You might say I am in my room. You are not also specific where exactly in your room. You are going to tell me on your bed. Okay, okay, you're on your bed. What are you really doing? What is your orientation? I am lying on the bed, because you can also be sitting. This is at least more specific. So if you say an electron is found in the shell, shell is not specific. Okay, so electrons are actually found in the shell. Shell is the same as saying the electron is in the house. Now, where exactly in the shell? It is going to be found in something which is known as a subshell. Okay, where exactly in this subshell? It's going to be found in what is known as an orbital. Okay, it is in an orbital. What is the orientation? It can either face the upward direction or the downward direction, up or down. So all these four things I've written here are known as quantum numbers. So when you are describing an electron, you say that an electron is in a shell. You need to describe the position of how the electron is using quantum numbers. Okay, using quantum numbers. So there are four quantum numbers that you must be able to know. And the first one that you can see, which I've written there as shell, first quantum number is known as the principal quantum number. The principal quantum number, the symbol that we use is n. So you can have n is equal to 1, n is equal to 2, n is equal to 3. The principal quantum number just describes the energy level or the shell. So the other name for shell is energy level. Okay, energy level. Now for each shell, remember we said the number of electrons in a shell is given by 2n squared. Not all the electrons in a shell are found in the same specific locality. That is why you are going to write something like this. In the same shell, you put two electrons there, two electrons here, because electrons are not going to be found all together, the eight of them. Okay, you know the principal quantum number is the shell number or the energy level. How about the subshell? The subshell gives what is known as the angular momentum quantum number. Angular momentum quantum number, this one is going to be represented by the symbol L. Now, the angular momentum quantum number is going to be a number that is going to be less than or equal to n minus 1. But this number, L, is always positive. Okay? Should always be positive. Let's say, for example, if I'm talking about the first energy level. First energy level, L should be numbers less than or equal to L minus 1. I mean n minus 1. So if n is 1, it means that L will be n minus 1, which is 0. We don't have any other number which is less than 0, which is positive. If n is 2, it means that L is going to be subtract 2 minus 1. Remember, look at this formula. Subtract 2 minus 1. That is going to give you a 1. So we're talking about all numbers less than 1 up to 0. Shouldn't include negative numbers, remember. So we're going to only have 0 and 1. So if your n is equal to 3, that is going to be L. If you subtract, L will be less than or equal to 3 minus 1, which is 2. So list all the numbers from 2 going down, but you shouldn't go beyond 0. So you are going to have 0, 1, and 2. If your n is equal to 4, your L, if you subtract 4 minus 1, it will give you 3. So all numbers from 0 up to 3. So L is going to be 0, 1, 2, and 3. So this is known as the angular momentum quantum number. The angular momentum quantum number just describes the shape of the sublevel. Okay? The shape of the sublevel. This is important. Shape of the sublevel. So meaning that for the first shell, it actually only has one sublevel. This one that you can see, one. Second shell has got these two sublevels. The third shell has got three sublevels like that. Fourth shell has got four sublevels. Now, each one of these have got a meaning, and that one you need to know. Every time you find L being equal to 0, that is an orbit. It has got the name. It has got a name. And how do you describe that? Because I'm talking about the first shell, you're always going to include the 1 in front. So I'm going to say 1. Every time L is 0, that is called an s orbital. S orbital. So for the second energy level, you can see we have got 0 and 1. When L is 0, that is called an s orbital. But because it's in the second energy level, we're going to put a 2 in front. So that will be 2s. When L is equal to 1, that is a p orbital. So we're also going to have 2p. If you go to n is equal to 3, because of the 3, we're always going to put a 3 in front. When L is 0, that is going to be S. When L is 1, that is going to be P. When L is 2, that is a D orbital. And then for the next one, when N is equal to 4, so we're going to have 4 in front. When L is 0, that is S orbital. L is 1, that is P orbital. L is 2, that is D orbital. When L is 3, that is so we call it as the SPDFG. We only end at G. If I had written n is equal to 5, we would have written 5s, 5p, 5d, 5f, and 5g. So these are the orbitals. This tells you that the first shell on you has got an s orbital. So you don't have 1p. It doesn't exist. They can give you this and then they ask you to say identify what is wrong on the following. You don't have 1p. Also for the 2, you don't have 2d. D only starts at 3. Also for the 3, you don't have 3f. Okay, so these are the orbitals. Now, when the s orbital, the shape of this orbital is just oval. there's one exam which they just gave, right? Draw the following orbitals. It's just oval like a circle. And then the p orbital is like the symbol infinity. Now the p orbitals, they are going to be the three of them. You're going to have px, py, and pz. This just depends on the plane in which that orbital is. Let's say this is the y-axis, this is the x-axis, and then you have got also the z-axis. So px will go like this. Makes the symbol infinity, but it is going towards the x-axis like that. And then for py to be going towards the y-axis, so it will be like this. And then for pz to be going towards the z-axis, so it's going to be like this. Okay, so that is the symbol. In other words, the symbol for p is just the symbol infinite like that. Can either point up, slant, depending whether it's py, pz, or px. So I can write it down here. P, the symbol is like that, or it can even be like that. And then for a d orbital, the d orbital is a bit of interesting. It also looks like infinity. But a d orbital, there are different d orbitals that you need to know. So there is dyz and dyz. Okay, the appearance of these guys are a bit of weird the way they look. Okay. You also have dxy. You also have dxz. In other words, you are just combining the x-axis, the y-axis, the z-axis. So these are some. Let me write this actually on the next page so that it can be that clear. I just have to state this because you just don't know what is on the examiner's mind. Okay, so we are saying we are going to have d, y, z. We are going to have d, uh, y, x, x, y, and those. Let me admit first. Okay, so we are saying we are also going to have d, x, y, and then we are going to have d, x, z. So how are these going to look like? So if you look at dxy, let's say this is the z-axis, and then this is the y-axis. The way these guys are going to be able to move is they'll just move in a direction that is away from what has been mentioned. So if x and y are the ones which have been mentioned, it means z will be alone. So the way this one is going to look is going to go like this, something like that, and then it also go like this. Okay, it's z is like, think of it as a propeller. And then those things we used to play with when we are children, you are holding your hand here, and then you are running with this kind of thing, and then it is spinning. So the one that has not been mentioned is more like the one where your hand is going to be holding. If you talk about dxz, so dxz, the only thing that changes is that what has not been mentioned here is y. So y, what has not been mentioned, is the one where you'll be holding your hand. For dyz, what has not been mentioned is the x. So x will be the one where you'll not be holding your hand. But if you want to maintain like your x being here, okay, let's say this is your y and then your z somewhere here, you can also write this, but just make sure that it will look like this is where you're holding. So something like that. But it's more trick the way it's going to look when you write it like this. Okay, something like this. You've seen the way this one is different from this one. It looks, so I'm holding my hand here and then I'm playing with this camera toy when I'm moving like that. Okay, I hope it just makes sense, but that is the idea. You can also Google you can Google these pictures so that you just see how they are going to look like. But that is how you get to write them. They are not the only d orbitals that we have. We also have something which is known as dz squared. But for dz squared, this orbital, let's say this is the x-axis, and then this is the z-axis. You also have the y-axis there. The way this one looks is you just follow the z, the same one which has been given. It looks like that. And then here now it's more like you write circles here. Okay, so that is the dz squared. And then the last one is d x squared minus y squared. So for this one, look at what has been named here. It's x and y. Z has not been named. So the one that has not been named is the one which will just be alone. So let's say this is the y-axis, this is the x-axis, this is the z-axis. So these ones will be moving along the y, the one mentioned, and along the x, the one mentioned, like that. So the z will just be alone. There are a bit of trick when you are drawing like that. But anyway, just know, at least know. I've seen questions where they've asked, draw this orbital. So this one we are saying it will be like so, going along the y because y has been mentioned, and also it will go along the x. But we best write it like this so that it can be much smarter. Let me write it again. Okay, we'll write this as y, this as x, and then z on top. So it will be like this, then like that. Okay, like that. So it's something not to worry very much about, but just know, at least have some ideas like that. So this is what is known as the angular momentum quantum number. It just describes the shape of the sublevel within an energy level. So I've got S, P, D, F like that. Okay. And then we come now to the orbital. So there is a difference between an orbital and an orbit. Orbit is the path taken by an electron as it moves around the nucleus of an atom. Orbital is the specific position. Now, we don't say specific, they can actually ask you to define what an orbital is. An orbital is a region around the nucleus of an atom where the probability of finding an electron is maximum. You use the word probability. Most of the times, an electron will be found in an orbital. Okay? The region around the nucleus of an atom where the probability of finding an electron is maximum. That's an orbital. Now, one thing you need to know is that each orbital can only have two electrons. Only two. So when you have got s orbital, it means you only have two electrons there. But here we have got when you have got an s orbital, let me write this. S orbital can only have two electrons. A p orbital, remember for the p we said that you have got, oh, this is actually what I'm supposed to talk about on the next quantum number. So after the angular momentum quantum number, now we're going to go to what is known as the orbitals there. And that is known as the magnetic quantum number. The magnetic quantum number, this one is going to describe the orbital that is related to a sublevel. So after a sublevel, we're going to have an orbital. How do you find the magnetic quantum number? Magnetic quantum number is represented by m with an L down. So magnetic quantum number is a number between L, negative L and positive L. Negative L to positive L. Okay, so let's say when L is equal to 0, it means that ML will also just be 0. And when L is equal to 1, it means that ML will be numbers from negative 1 to positive 1. So negative 1, 0, and 1. If your L is equal to 2, it means that your ML from negative 2 to positive 2. So that will be negative 2, negative 1, 0, 1, and 2. So each of these numbers which I'm writing here represents an orbital. So meaning that for L is equal to 0, remember L is equal to 0, what orbital is that? Is the s orbital. So the s orbital only has got one orbital. And then when L is equal to 1, this is the p orbital. P orbital has got how many orbitals? Three of them. Look at this. One, two, three. And then when L is equal to 2, that is a d orbital. A d orbital has got how many orbitals? One, suborbitals, two, three, four, and five. And we are saying that each orbital can have two electrons, meaning that for the first energy level, because it only has one orbital, it can only have two electrons. For the second energy level, it has got orbitals. So it can have how many electrons? It can have six here. But now, this is not the second energy level. Okay? Let me make you understand this. Let's now write it properly. Let me start when when n is equal to 1, this is the first energy level. We want to find first the angular momentum quantum number. What will be L? L will only be 0. Remember, it is n minus 1. And when L is 0, that means that ML is going to be equal to what? Is only going to be equal to 0. Remember, when L is 0, this is s orbital. So this is 1s. Okay. And the appearance, this orbital is just like this. This is how you show an orbital. So it can only have who? Two electrons. When n is equal to 2, remember we said L is a number from 0 all the way to n minus 1. So L, you are going to have L being equal to 0 and L being equal to 1. When L is equal to 0, this is the s orbital, but it's in the second energy level, this is going to be 2s. When L is equal to 1, this is going to be a p orbital. It's in the second, that is a 2p. Now remember, we said that when L is equal to 0, what will be ML? ML is just a number from 0 to what? I mean from negative L to positive L. And that will just be 0. So meaning that this is only one orbital. When L is 1, we say that ML is a number from negative 1 to positive 1. So we're going to have negative 1, 0, and 1. The meaning of this is that you have got three orbitals which are together. So in total, the second energy level has got four orbitals. This one, and these three. That is why the second energy level can have 8 electrons, because each of these orbitals can have 2 electrons. If we go to the third energy level, n is equal to 3. We said that L can be 0, L can be 1, L can be 2. When L is 0, ML is also just going to be 0. And this orbital is just 1 like this. When L is negative 1, it means that ML is going to be equal to negative 1, 0, and positive 1, meaning that you have got three orbitals in 1. When L is 2, it means that ML is going to be negative 2, negative 1, 0, 1, and 2. So how many are there? There are 5 orbitals there. So they're going to be 5 in 1. 1, 2, 3, 4, and 5. Remember, when L is 1, this is an s orbital, so this is the 3s. When L is, I mean, when L is 0 is s. When L is 1 is p, so this is going to be 3p. When L is 2, that is d, so this is going to be 3d. So the meaning of this is that for the third energy level, how many orbitals in total does it have? 1 plus a 3, 4 plus 5. That is 9. That is why the third energy level can have 18 electrons, because each orbital can have 2 electrons. So these are the three quantum numbers. The last quantum number, which is representing now the direction of an electron, whether the electron is pointing up or pointing up, down, that is known as the electron spin. Electron spin quantum number represented by m with s. So if an electron is in an orbital, an electron will use an arrow, one arrow with one head like that, or even two heads, it doesn't matter. So when an electron points up, it means its spin is positive 1 over 2. If an electron points down, its spin is negative 1 over 2. Okay, now having understood this, let me show you how you apply this. Let's say you've been given an electron written as 3d4. What does this mean? Describe the four quantum numbers describing this electron. So the first one that you can see is the principal quantum number. The principal quantum number here is just a number in front, so the principal quantum number is a 3. The next quantum number is known as the angular momentum quantum number, represented by L, and that is given by D. But every time you see D, what angular momentum quantum number is that? Remember I said when L is 0, that is S, L is 1, that is P, L is 2, that is D. So meaning that because this is D, it means that L is going to be equal to what? 2. Now to find ML, we know that ML is given by negative to negative L to positive L. So L is 2. So you are going to have negative 2, negative 1, 0, 1, and 2. Remember we said that each one of these numbers is representing an orbital. So negative 2 is an orbital, negative 1 is an orbital, 0 is an orbital, 1 is an orbital, and 2 is an orbital, like that. So the meaning of these 4 means that we are talking about the fourth electron. Now when you are putting electrons in these orbitals, there are two rules that you use. Okay, there are two rules that you are going to be able to use to be able to fill orbitals with electrons. The first one is known as the off-Bohr's principle. There are actually three, not two. The first one is the off-Bohr's principle, the second one is Pauli's exclusion principle, and the Hand's rule. So this is where we even end. I'll continue from here in the next class. Also talk about this so that you just understand. So Pauli's exclusion principle, and then off-Bohr's rule, and then Hand's rule. Now, starting with Pauli's exclusion principle, it says that every electron has a set of 4 unique quantum numbers. So by the Pauli's exclusion principle, it means that you can't have two electrons which can point in the same direction in the same orbital. And then the off-Bohr's rule is going to tell us that when you are filling electrons, fill them first single before you can fill them. Actually, the one I'm talking about is Hand's rule. Hand's rule will tell you that when you are filling these orbitals, first fill them with 1 electron before you can fill them with 2 electrons. Off-Bohr's rule is going to tell you that when you are filling an electron, you first fill electrons to the orbitals with lower energy. You understand this one very much as we talk about electron configuration. So here, because we're talking about 4 electrons, you first fill these electrons in the same direction. So the first electron will be up, second electron up, third electron up, fourth electron up. So look at where the fourth electron is. This means that ML, in which orbital is that? The fourth electron is in ML being equal to 1. And what is its direction? That will be the electron spin. It is up, so that is positive 1 over 2. That is how you write the 4 quantum numbers. Okay, let me change. Imagine on top here we didn't have D. I mean we didn't have 4. Imagine we had 7. So the meaning of this would be, okay, let me say we had 6. So fill the 6 electrons, but you first fill them, each orbital fill it 1 1, and the electrons should all be pointing up. So the first one here 1, second one here 2, third one here 3, fourth one here 4, 5. After you are done filling the sixth one, now start again, but it should be pointing down. So 6 should point down like this. So meaning that ML is falling, the sixth electron is falling in negative 2, and it is having a downward direction, so that will be the electron spin is -1/2. Okay, let me not exhaust you. We'll continue from here in the next class and talk about, so in the next class we'll talk about electron configuration, orbital diagrams, also talk about properties of or periodic trends like ionization energy, what else, ionization energy, the atomic mass, and the electronegativity. So basically properties, ionic size, properties of the periodic table. Those are the things we'll talk about in the next class. So let's end here today.